Okay, so today we're talking about unbalanced forces. So far, we have essentially tried to keep those torques that we've been dealing with balanced in this class. We've been dealing with static equilibrium, trying to keep objects from rotating. But in the last lesson, we learned about rotational kinematics. Obviously, things were rotating back then. They were accelerating, they were moving. So we need to start talking about how we deal with those torques that cause those things to rotate. Well, there's a pretty solid linear analogy here that is basically just like unbalanced torques. And it's unbalanced forces, right? If a torque is just a force that causes something to rotate, then we can start by looking at how we dealt with forces way back at the beginning of the year. How did we deal with unbalanced forces? We looked at them through this equation here. Net force equals mass times acceleration. Okay, well, our job today here is going to be to take this equation and essentially translate it into a rotational version. We're just going to take it and turn it into its rotational version. How are we going to do that? Well, we're going to look here first. I want you to imagine that I have a mass over here at the end of a massless, rigid rod, which has a radius of r, and we're applying a force F to it in the upwards direction. This is a torque, right? This is causing our object to rotate. So let's look back over to the left here where I've got my net force equals ma. I've swapped it out for just F rather than net F because, well, there's only one force. So that force would be equal to the mass times acceleration of this object. So I'm just going to take this equation here and swap it out and translate it into a rotational analogy. And it looks like this. The first thing we're going to do is we're going to look at this right side over here. We're going to say, well, we need to swap these into rotational variables. Mass isn't necessarily a linear or rotational variable in and of itself. So we're just going to keep that there. But acceleration, that acceleration there, that's a linear acceleration. We got to turn that into a rotational acceleration. Luckily, we know how to do that. We know that linear acceleration, or translational acceleration in this case, is equal to r times angular acceleration. So my first step in translating this over here is I am going to just swap out that acceleration. I'm going to say that force is equal to mass times radius times angular acceleration. Okay, so now on the right side we have essentially all rotational variables. So let's look at the left side. Force, that's a linear variable. It is a straight line vector. It's a linear variable. How do we turn it into a rotational variable? Well, the analogous to force in a rotational world is torque. How do we get from force to torque? We're going to multiply it by r, the radius of the lever arm, or the length of the lever arm. So multiply both sides by r. It's going to look like this. And then I'll swap things out. So r times F, that is torque, equals m r squared alpha. Okay. Well, this is pretty helpful, but I guess it's not very generalized, right? At this point, this is an equation for a specific situation that we're looking at here on the board, where there is one object at the end of a rod that a force is being applied to rotate it. So what if there were something like this? Well, now I've got multiple objects at the end of the rod where multiple forces are being applied. So I need to kind of take what I had back then, this torque equals mr squared alpha, and expand it and generalize it and say, okay, well, if I have multiple torques, then I'm going to have to take the summation of all those torques. I'm going to have to take the net torque. And if I have multiple masses, well, I'm going to have to sum up all of those masses times their radii squared. and then I'll multiply that times the angular acceleration of the system as a whole. Okay? Now we've got it in a better spot here. This thing here, though, let's talk about that. That there, I'm actually going to swap out with its own variable. We're going to use the letter I to represent this idea. And I represents something called rotational inertia. That is rotational inertia. We'll talk about an exact definition for that in just a second, but I want to be clear. Our net torque equation looks like this. So the net torque on an object is equal to the rotational inertia times alpha. All right? All right, let's check out our definition here for rotational inertia. It looks like this. Rotational inertia is an object's resistance to changes in its rotational motion. That's it. I mean, it's basically just like normal inertia, right? Inertia is an object's resistance to changes in its motion. So rotational inertia is an object's resistance to changes in its rotational motion. Now, on the previous page, we used this equation here to figure out an object's rotational inertia. And it's a helpful equation, but it's only a helpful equation when it comes to point masses and stuff like that. Like if I had a disk that was spinning like this, I couldn't necessarily find the mass and radius of this object. Why? Because I would have to do this equation here for every single particle, every single dot within this disk, and that would take me a long, long time. So we actually have a solution for that, and we'll get to it in just a second, but I want to provide you with an example of rotational inertia kind of in a basic form. I want you to imagine I had 2 meter sticks. Here's 1 meter stick. Here's the other meter stick. And let's say I placed those meter sticks up against the wall so that the very bottom of them was hitting the corner of the wall. And on this meter stick, we'll call this meter stick A, and this one B. I put a bunch of mass, let's say like 3 kilograms worth of mass. And then I let the objects drop. They're going to rotate at the bottom here, at this axis, because of the corner of the wall. And the question is, which one's going to hit the ground first? Well, our answer is actually going to be B. B is going to hit the ground first. Why? Because of this mass over here on A, this object's rotational inertia is going to increase. It's going to be larger than B. So it is going to be more resistant to changes in its rotational motion. It's going to be easier to get B to rotate. So therefore, it is going to hit the ground first. It is going to take less time to get up to speed, and therefore it'll hit the ground first. Okay, let's do a quick mathematic example related to that. Again, here we're going to use this rotational inertia equation, the sum of the mr squareds. Again, this only works for point masses, like we're looking at here. We got 2 situations. I'll focus here on the left first, this example A. We have this massless rod, which has 2 masses, 2 point masses on it. One is 5 kilograms, one is 7 kilograms, and it's rotating about its center. Then over here at B, for example B, it's the same rod, same masses, just this time I've moved the pivot point all the way to the left, the far end of the rod. And I need to figure out the rotational inertia for these objects here. So for A, we're going to take the sum of all the mr squareds. So that is going to be 5 times the radius from the pivot point for that 5 kilogram mass was 2, and then 7, and again the radius for there was also 2. Plug those into my calculator real quick. We're going to get 20 plus 28. So the total rotational inertia will be 48, and here's actually the units for rotational inertia, 48 kilogram meters square. I know we didn't talk about that before, but that's what our units are going to look like. Then over here, we have the sum of the MR squareds for example B. Let's just get a refresher of what that looks like. So we have two masses. One is 0.5 away, 0.5 meters from the pivot point. The other is 4.5 meters from the pivot point. So we have mass of 5, pivot point is 0.5 meters away, square that, plus 7 times 4.5 squared. Plug those into our calculator. Let's see. So 0.5 squared times 5 is going to be 1.25. And then 4.5 squared times 7 is going to be 141.75. Add those two together. We are going to get rotational inertia equals 143 kilogram meters squared. Cool. Not too bad. Not too bad. Now we're going to go back to what I was talking about before about that disk. Remember that the equation we were using up at the top of this page only works for point masses on essentially massless objects. But if I had a disk or a hoop that was going to rotate, I would need to take the mass and radii of every single particle inside. That would be a lot of work. Luckily, people have already done that work for us, and they created this chart here. This is a chart of all the most common rotating objects that you might see in AP Physics 1. The good news is that you don't have to memorize any of these equations. Here, let me highlight them in case you can't find them. These are the equations I'm talking about. So these were found by other people. There is a calculus equation to solve for them. And again, you're not going to need to memorize them. If you ever need them in the future, they'll be told to you. Just figure you should know this is coming. All right, let's use this in an example. Let's say that I have a disc and a hoop, and I've placed that disc and hoop at the top of a ramp. So I've got a disc and a hoop. Let's say that the mass of the disc is equal to the mass of the hoop, and the radius of the disc is equal to the radius of the hoop. So they're both the same size and shape, essentially, with the same amount of mass, just one is a hoop and one is a disc. The question is, which is going to hit the bottom first? Who is going to win this race between the disc and the hoop? Well, to answer that question, we have to go back here. We are going to look specifically at these two equations here. So here we have a hoop about a cylinder axis. So that is, here is our hoop. It has a rotational inertia of mr squared. Meanwhile, the disk has a rotational inertia of 1/2 mr squared. That's right on the bottom there. So, which one has more rotational inertia? It's going to be the hoop. So that one's going to be slower to move at the bottom of, slower to get moving at the top of the ramp. So, which one's going to hit the bottom of the ramp first? The winner in this case is going to be the disk. The disk will win because it has less rotational inertia, as shown in those equations previous. All right. Last thing we got to do. I have got a practice problem for us here. Looks like this. Most of the time in this class, we have dealt with massless, frictionless pulleys. That's because it makes our math easier. But luckily, now you know how to deal with it with a pulley if it does have mass and friction. You're welcome. But this is the example I have for you here. It's called a heavy pulley problem. On the right, I have drawn a pulley. You can see it has a radius of 33 centimeters. I have a string wrapped around that pulley, and I am pulling down with a force of tension on that string, getting this pulley to spin. I also know that the mass of the pulley is 4 kilograms. And there is a force of friction between the axle and the pulley itself. Other information I've been told, I know that this pulley starts at rest and then speeds up to 30 radians per second over the course of 3 seconds. I also know that the torque from friction is about 1.1 Newton meters, and the force of tension in the rope is about 15 newtons. Okay, that's a lot of information. The question we're trying to answer is, what is the rotational inertia of this pulley? Now, you might think we can just use the equation for a rotating disc like we did over here to answer that. Unfortunately, that's not going to work for us here. This pulley is more complicated than that. There's a small hole in it. There are divots within it. There's more going on than it just being a simple disc. So what are we going to have to do? We're going to have to kind of analyze it in a different way. We're going to have to look at it like this. We're going to have to say the net torque is equal to I alpha. And we're going to have to solve for I to figure out, to calculate it rather than just using one of those equations. How am I going to do that? Well, we know that there are two torques acting on it. We have a positive torque from tension and a negative torque from friction. That equals IA. We know the value of friction. We know the radius and force from tension. That's good. We're trying to solve for I, but we don't know alpha. Well, luckily, we were given different information, right? We were told that it starts from rest, speeds up to 30 radians per second over the course of 3 seconds. So I'm going to use some kinematic equations over here on the right to solve for acceleration. I'm going to say that we ended at 30 radians per second, started at 0, plus alpha times 3. So therefore, alpha is equal to 10. Okay, now I think I have enough information to solve for our answer here. Sorry, I should say 10 radians per second squared. Got to put your units. So back over here on the left, I'm going to start plugging in numbers. Our radius is 0.33. Our force is 15, like told to us on the previous page. We know that the torque from friction is 1.1. I is what we're solving for, times 10. Okay, take that all, plug it into a calculator. So 0.33 times 15 minus 1.1, divide that by 10. I get a rotational inertia of about 0.385 kilogram meters squared. There you go. There's our answer. Now, if you were to go back and take this equation here for the disc and plug in our variables for this pulley, you'd actually find you'd get a much different number, just to prove that I meant what I said when we needed to solve for it this way. So yeah, there you go. That's unbalanced torques. That's how we're going to deal with when you have a accelerating object and different amounts of torque acting on it in this class. Hope this was helpful.